Wait, there are a lot of online things there.
Yeah, hi everyone. Thanks for coming. Today we have Nicholas and Millard from Google Brain, and they're going to talk about their work auditing the privacy of ML model training. Let's welcome them.
Okay, thanks for having us. Just to check, you can all see the slides and everything?
Yes.
Yeah. Okay, very good. So the talk probably will last roughly 40-ish minutes. Milad and I will split it roughly down the middle. And we are happy to take sort of questions as they come. I can't see any of you, so please just interrupt as you want to ask various questions, because I won't be able to see anything you're saying. Okay. So the general setup for this talk is we're going to be considering machine learning models that are like increasingly being trained on private images. We have people training medical machine learning models on images of like cancer scans of patients. I'm sure you've all have seen, machine learning models being used to predict what word you want to type, and these are trained on the text messages that people type. You have the same thing with emails, where you have models predicting what the next words you want to type on, and these are trained on emails. And so you have these models that are being trained on lots of sensitive data, and you want to make sure that the models don't leak any of the sensitive data to users. But unfortunately, if you just train models naively, this is exactly what happens. If you just train a state-of-the-art machine learning model, on the left we have a vision model, on the right we have a text model, then it turns out that the models occasionally will find some of the examples from their training data sets and just completely omit them at generation time. So on the left, we have this state-of-the-art diffusion model. This image of a person was contained in the training data set with the caption, living in the light with anagram LUTs. And on the right, if you just ask the model for a picture of anagram LUTs, then it sort of gives you like this exact repetition from the training image. And on the right, we have an example of a similar thing happening, but for the case of a language model, where we asked GPT-2 for some fairly weird prefix, and it happened to decide to spit out the full name, email address, phone number, fax number of some person whose data was contained in the training data set.
Is this prefix attack? Is it like a targeted prefix, like you use some kind of gradient descent method to find the prefix, or you have some more complicated?
No. We randomly, for this one on the right, I took a random like 1 megabyte dump, like just piece of text from Common Crawl, and just chose 5 random words from the text, and then I just sampled using those 5 random words to give me the next 1,000 tokens, and I checked if any of those next 1,000 tokens looked like they were training examples, basically.
Oh, okay. That sounds pretty bad.
Yeah. Yeah. So like this is like, yeah. And on the left, it's a little more targeted. Like we asked the model in particular for this image of the person we knew was in the training data set, and it gave it to us. But like the general idea here is that we have these models that like are like, in a very real sense, the training objective of these models is to memorize the training data. Like you sort of look at like what models are actually trained to do. They're trained to memorize training data in some sense, and they do. And so you would not want to apply, like these models were trained on data that was public from the internet. And so it's fine. Like this picture is this person's Wikipedia bio photo. Like they've licensed it to be, Creative Commons, and it's on their Wikipedia, and like it's on all the talks they give them. So like it's not sensitive in any setting. But if this model were instead trained on medical images, and you can ask for, my medical scans, that would be bad. Same thing on the right. This was some document. This was like a crypto paper this person had put online, basically. And it sort of had some information for them. And so it's probably okay that maybe it's okay the model knows it. But like if this was trained on sensitive emails from a company, it would be bad if it memorized like information of like patient records or individual people who the company has worked with in the past or something like this. Okay, So this is just to set things up and to say that like this privacy problem is a real thing and we need to do something to stop it. So enter differential privacy, where this gives you a way to train models that are guaranteed to not leak their training data in this kind of way. I think you've heard some recent talks on differential privacy. Is that right?
Yeah.
Yeah.
Okay. So let me briefly sort of introduce. I'll also skim through the introduction, just because I think the framing will help explain what it is we're about to do. Yeah, so there are these differential privacy libraries. This is like the canonical technique that's used to train machine learning models. And you know, right, the setup, which sort of is the intuitive explanation that people always give, is right. You have two models. One of them is trained in world A with some set of emails. The other one is trained in world B with some set of emails, but one example is different. You like hide the original datasets, and you ask an adversary to guess like which model was trained on world A and which one was trained on world B. Is like this way or is it the other way around, right? Sort of this this is the game that Differentially is trying to protect. And bounds the probability that you can succeed at this game example. It's like a very, very worst case definition. And you know, like if less than some threshold, I mean it's parameterized by epsilon. When epsilon is 0, you can basically never win. If epsilon's infinity, you can win always. Epsilon 1 is like, I don't know, roughly half-ish or something like that percent of the time. And so the idea is you want to train with like a low epsilon in order to make the thing be private, but it's very hard to understand what this like low epsilon actually means in practice. Okay, and so you can imagine the amount of privacy that we have is like, you have a training algorithm which is differentially private. There's like the upper bound guarantee, like which is like by differential privacy, we know that the leakage can't be more than this because we have a proof that says it's not. We have some real amount of memorization that actually is going on in the model. Maybe we can't account for it in our analysis. The analysis techniques might not be enough. And so it's a little bit less. And in this talk, I'm going to show you how to do a lower bound, where we know that so we can say like there's more memorization than this. And the hope is that we'll be able to have a fairly tight lower bound that constrains reality. Reality is somewhere very close in between these, the upper bound by DP and the lower bound from what we're going to cover in this talk. Okay. So the way that we're going to do this is we're basically just going to actually build this adversary that does this guessing game. Like the DP definition has some hypothetical adversary who has to distinguish between being trained in world A or in world B. We're just going to actually build the adversary that distinguishes here. And once you have a concrete adversary, you can directly convert this into an epsilon value. And so it's sort of very straightforward. The math is sort of very easy, and we'll get to some more complicated things once Milad starts talking. But to begin with, it's sort of a very, very easy conversion to do. Okay. Let me briefly just set up some motivation for why it is that you might actually want to do this kind of auditing. I think there are roughly
ask a question about the setup?
Yeah, go ahead.
So is A and B are neighboring? Like your goal is it to distinguish neighboring database?
Yes, correct.
So the database is it like a set of user records? Like, what should I think of? Is it a set of user records?
Yeah, you can think of a training data set and a training data set where I've added this like one red email example.
I see.
So there are two training data sets. They're identical in every way, but my data is in one of the training data sets and not the other.
I see. Yeah, thank you.
Yeah, other questions? Okay. So why is it that we should do this auditing in the first place? I already gave you one of the reasons we might care about it, where we might want to know like how tight is the bound. You can imagine one world where maybe the DP the analysis is very, very tight and sort of perfectly characterizes where we are. Or you can imagine that the DP analysis is like very, very loose, and there's like a lot of room that we could improve the analysis and there's sort of a very big gap between the lower bound and the upper bound. This is one reason why we might want to develop some kind of auditing techniques. You also might be curious to analyze the algorithm under different settings. DP only gives you a guarantee for like the worst case possible data set you might ever see, with the example that like is the worst case example for that worst case data set. But like we train our models on like ImageNet. Like, is that actually what happens? Like, is our models trained on ImageNet like more private in some sense because the data is not out to get us? Or is it actually just this worst case world we're living in? You could also might want to know, like, what if we could make some new assumption? Like maybe we assume that our adversary cannot do a certain kind of thing. It might be very hard to analyze this formally, but you can add this new assumption into your attack and prevent the adversary from doing something. Maybe this lets you analyze what this might be able to gain you if you add a new assumption. Conversely, you might have the setting where you might be able to show, even with this new assumption, the attack does not get any worse, in which case the assumption probably is not useful and it's not worth doing the analysis for. And finally, you can actually use these kinds of things to empirically validate the correctness of some piece of code. Right? There's a very nice quote by Knuth I like, beware bugs in the above code. I've only proved it correct, not tried it. And we've had examples of papers, like last year, some people put a paper on arXiv where they had a very nice proof that their algorithm was correct. It was DP with epsilon like 0.8 or something. And we took their algorithm, that they had sort of, they had code, we took their code, we ran this auditing framework I'm about to present to you, and we showed that the auditing framework showed a lower bound of epsilon of 2.3, which means they made a mistake in their analysis. And it turns out we found out what was wrong. They had a division, and they didn't divide by a batch size somewhere. And so you can have these cases where you think that you've gotten everything really right. You've tried very, very hard to prove something, but you've made a mistake. And this kind of auditing can help find these kinds of bugs. Okay, so that's basically the setup. Let me briefly introduce you to the way that you make a machine learning model private with DP HTT. First, though, let me tell what stochastic gradient descent is, or SGD, which is this is how we train a machine learning model. Well, all you do is like a very simple algorithm. You take a batch of examples, we'll call the batch of examples Z, from your training data set. You compute the gradient with respect to the model parameters of each example under some loss function. Maybe this is like reconstruction loss or cross entropy of some classifier or something like that. You compute the average of the gradients, and then you take a step in the direction of the average gradient. It's like a very simple algorithm. There's nothing complicated to it at all. DP HTT makes only two very slight changes. The first change that it makes is it clips the per example gradients. This sort of bounds the sensitivity of each of the gradients. And then you just add Gaussian noise after you compute the average. So DP HTT as an algorithm is like exceptionally simple. You just take DP HTT, you add these two steps, and all of a sudden you sort of get privacy from that. Okay, and so in this talk, we're going to audit DP HTT in order to understand how private this algorithm actually is. Okay, so let's get started by talking about how this is going to work. In particular, we're going to construct two adversaries. We're going to construct the first adversary, which is we're going to call the crafter. The crafter is going to create two data sets, A and B. They differ by one example. They're sort of identical and adjacent except for one example. And then we have a distinguisher, which is going to then take a model and guess if the model came from A or B. So the crafter gets to construct the data sets. The distinguisher knows what A and B is, but they don't know whether the model was trained on A or B. Okay, so here's sort of the protocol. The adversary initially crafts some data set A and B. The model sends both of them to the model trainer. The model trainer flips a coin, chooses either A or B, trains a model on that data set, and then sends the model F to the adversary. The distinguisher then guesses if F was trained on A or B and wins if they got it right and loses if they get it wrong. And so the way that you can convert this into a DP guarantee or into like a DP lower bound is you sort of take this whole protocol, you like stick it in a box, and you repeat this many, many, many times, like in particular thousands of times. And then you can compute the probability that you succeed and the probability that you fail, and you can use this to give some number of epsilon, whatever the number is going to work out to be. Okay. So far, does everything make sense?
Yeah.
Okay, very good. Okay, so let's start with the simplest version of the protocol you can imagine, which basically is like membership inference. I don't know why I had those lines there. Okay. Okay, so what we're going to do is we're going to take some standard existing data set, like MNIST. That's going to be, well, the crafter's going to call it dataset A. They're not going to do anything fancy here. They're just going to take, say, just any normal data set. Dataset B, they're going to take this data set, and they're just going to add a single example from the test set. These two data sets are adjacent because you're just taking a normal data set and adding one example, and this is all they're going to do. Then what the distinguisher is going to do is a very simple thing. It's going to look at the most likely output of the model when you classify on this label 7. What I mean by this, I mean is f of x is going to give you a distribution, a probability distribution over each of the 10 images. In this case, I'm going to ask for like, what is the most likely output? This probably corresponds to label 7. And you might say that the model says that the likelihood of this image being a 7 is like 95%. In world A, let's sort of imagine world A, it's probably like something that's like 95%. If in case though we were in world B, it might be something like 99.9%, because the model saw this exact image during training, and so it's more likely to get it right. So all the distinguisher is going to do is that they're going to set a single threshold, and they're going to say if the likelihood of this example is greater than some number, let's say 0.999, they're going to guess yes, otherwise they're going to guess no. And then you can convert this into a DP guarantee or a DP lower bound. And if you run this, if you run an algorithm that's actually epsilon3 private, this does quite poorly. Like the empirical lower bound of epsilon you get is like not quite 0, but almost. It's like, I don't remember, 0.2 or something. Okay, does this setup make sense? Because this is like the foundation we're going to use for all other future attacks.
Can you explain what are the two bars? What's DP and MI?
I see, yes, okay. This is the upper bound that DP gives you. Like, so let's train an algorithm, let's repeat this game with differential privacy of epsilon equal to 3. MI is what is the empirical lower bound we can actually observe, given the fact that we trained this model, that was sort of running this actual attack, trying to instantiate this game.
Yes, thanks. I guess DP is the theoretical analysis and MI is your attack. That's what you're saying.
Yeah, MI is this membership inference first attack. Does this make sense? Like, because if this doesn't make sense,
yeah, it makes sense. I was just confused what DP and MI stand for, but now I see.
It's going to get even more confusing. I'll make sure that we're good so far. Yes, no.
I guess so your MI can basically, it doesn't match the theoretical. Like your MI, I mean, this is just like some arbitrary attack, so it's not as powerful.
Yes, yeah, this is a single attack. It is a very weak attack because we're taking this membership inference game where we're comparing a normal data set to a normal data set with a random test image. And so like we're not taking full advantage of the attack assumptions. And because of that, the lower bound we get is fairly weak.
So as a sort of follow-up to that, would this lower bound still be valid if you based your threshold on the observed values? Or would that sort of break the DP guarantee that's given?
Yeah, okay, very good. Okay, so if you base your threshold on the observed values, it does break the guarantee. So what you have to do is you have to run this game twice. The first, you sort of run a setup phase, and then you pick a threshold, and then you throw away everything you've done, and you repeat it all over again. And then you sort of use that threshold you picked the first time around.
Yeah, so the adversary sort of can't be adaptive to, like that wouldn't.
Correct.
Okay.
Yeah, that would be cheating. In practice, this just means you train twice as many models as you would otherwise have done. The first time to choose a threshold, the second time to actually run the game. And this is part of the reason why it's so expensive to do this. Is like we need to train thousands of models in order to be able to get these kinds of guarantees. Very slow. And Milad's part of the talk, he'll tell you how to fix all of that.
Wait, the theoretical guarantee allows the adversary to choose the threshold based on some like It's just running based on empirically running the experiment many times. The
Right.
theoretical guarantee allows that.
Correct.
But your practical
So
attack is not using that, or is using that? I'm confused.
It is using that. So we would first train many models to figure out what the threshold would be. And then we go and train a bunch more models in order to actually run this sort of game to train a bunch of models and see what we actually get for this. Okay, so let me maybe back up and just repeat things from from the beginning, what we're going to do. So like we have this sort of game where we run this one round of a distinguishing thing. In practice, what we're actually going to do is we're going to repeat this many times, let's say 1,000 times. After we've repeated this like 1,000 times, we can then figure out what would have been the best threshold for us to pick. Maybe the best threshold was like 0.998. Now that's cheating because we've used like adaptively this sort of interactive thing to pick the best threshold. So we can't actually use that number right now. You then have this number in mind, and then you say, okay, let's go back to the beginning and let's rerun our thing from the very beginning using this threshold of 0.998. And then we train many more models again. And now we can use this to get some kind of to get some kind of lower bound using the information we learned from the first time we ran it, but not actually using an adaptively chosen threshold from the second time we're running this whole protocol. How are we feeling?
It's a little bit lagging.
Are people feeling okay so far then?
Yes.
Okay. Okay, so let's sort of make the assumptions now a little more realistic. Instead of a worst case, instead of this like simple case, we're going to construct like a worst case data set, like a worst case distinguishing attack. What we're going to do is we're going to take the same MNIST data set, but instead of adding a random image from the test set, we're going to add like an adversarial example, like something the model is going to get very, very wrong, so that we can maximally, hopefully, distinguish between these two cases. And the reason why this should help is that if the model didn't see this adversarial example during training, it's probably going to assign it exceptionally low confidence. This is sort of what the input was designed to do, is to have low confidence. But if the model did see it during training, then it will have relatively high confidence. It's not going to be really high, but it's going to be much higher than if it hadn't seen it. And this allows us to distinguish between these two worlds with much, much higher accuracy. And so instead of being in this membership inference world where the epsilon lower bound we get is very, very low, like we get like a much tighter analysis by picking this worst case example. Okay. So I haven't really done very much here. I've just sort of made the example worst case and I get like a tighter analysis. Let's like continue refining the analysis now. DP HTT makes the DP analysis makes many assumptions, one of which is you have intermediate access to the model. So you can have not only access to the final trained model, but DP analysis assumes that I get to see every single intermediate step of the computation. And so this gives the adversary a lot more power. What it means is that instead of the model trainer sending back just this model, they send back like all of the sequences of models that they ever saw during training. And so now what the adversary can do is they can basically compute the average over all of these models that they see, like F1, F2, F3, F4, all up to the end. And this gives you a much better predictive power to be able to succeed more often because there's less randomness going on here when you average over all of these models. So again, we're sort of making use of one more assumption of DP HTT, and the analysis like gets even tighter. Mm-hmm. And the final thing that we can do is the analysis makes even one final assumption. The analysis is assuming not only that we can control the data sets, like it turns out that the analysis, if you actually dig into what's doing, the analysis assumes, that the adversary actually has the ability to control the gradients that go into the optimizer. Like the thing that was made private, the privatized object, was not the input to the model, but was the gradient update. And so you can imagine an adversary, like a hypothetical adversary, who for some reason could control gradients, maybe if we're in federated learning or just trying to audit. And you can use this to make the analysis even tighter by constructing not the setting where you send two datasets A and B and you get back a model F, but like the adversary constructs gradient updates, gradient update A and gradient update B, sends them to the model, applies these to the current model, and then sends back the model that was either using gradient update A or gradient update B. And when you do this, it turns out that like things get really, really like it's sort of essentially a perfect auditing if you allow this kind of gradient update. So most of these figures have been like somewhat lies. Here's like the actual figure from the paper where I'm showing you the same thing where we train a model with epsilon 2. This is the the theoretical upper bound. And as you vary the amount of attack assumptions, you can get the you can see how we can increase the lower bound from something like very close to 0 to something that's very close to 2. What I'm showing here is the blue bar is the epsilon value that you might get, but we don't have sort of statistical confidence in the result. The solid line is the margin of error. You should notice the margin of error is sort of very large. Even with training like 10,000 or so models, like the margin of error is enormous. And so like part of the reason that auditing is hard is because you have to do training many models, because each time you only learn like one bit success or fail. And in order to make sure that you actually are correct more often, or like you actually are confident in your answer, you have this very large margin of error.
I didn't understand the last one where you said the adversary can choose the gradient. Is this still a DP notion? Are you saying the paper's proof something stronger that it satisfies DP even if it's an active adversary? Like, is it because of that?
Yes. So let's go back to hear what DP HTT actually does. DP HTT takes like what is made private in DP HTT. What we're adding noise to is the gradient vector, which results from a particular training image. But DP doesn't know anything about the fact that this was a gradient vector. It doesn't know we averaged anything. What is made private are these gradient, are like these like list of numbers. We just clip them and add noise. So like as far as the analysis here is concerned, this gradient update doesn't matter whether it acts from the gradient of a model or whether it was like selected in the worst case by an adversary. And so like the analysis assumes in some very real sense that the adversary could have maliciously modified the gradients themselves.
It's a question in the chat.
Yeah, could you read it out? I can't see the chat.
Yes. Does this adversarial gradient also get clipped and noise added to it?
Yes, of course. Yeah. You have to make sure that like the adversary. So the protocol that's run is we take a gradient, we clip it, and then we add noise. And if you don't do that, of course you can like trivially do this. Yeah, like the DP HTT sort of this is what's made private. The gradients are made private via clipping and then noising.
I guess maybe the confusion is about the system model. Like, is the adversary like sitting on the client side? If it can tamper with the gradient and before the clipping happens, that means the adversary is on the client side, right?
Yeah. So the actual adversary that exists in order to make this gradient thing make sense is like a very strange adversary. So this fairy tale thing that probably doesn't actually exist in practice, but is the analysis assumes the existence of this very strong adversary who can do this thing. And so we show that if you make the assumptions that the analysis is doing, then you get a fairly tight auditing. Now, yeah, of course, the settings in which this adversary actually does exist are probably very limited. So this probably isn't actually what you need to defend against, but DP HTT assumes that this person exists. Milad is actually going to tell you quite a bit about like how you don't actually need this assumption. So yeah.
So all existing DP analysis uses this assumption, even though like typically when you think of DP, you think of the definition of differing by one data set, by one data point in the training set.
The analysis, yeah, all analysis for DP HTT uses this.
That's okay. That's really interesting. This is like a significantly stronger adversary.
Yeah. Yeah, so, right. So basically what this plot is showing you, what's so nice about this plot, is it shows you that, you know, if you didn't make this assumption, maybe it could be the case that you could make the analysis quite a bit tighter. Now, Milad is actually going to spoil his talk a little bit and tell you how this is not going to allow you to make the analysis that much tighter. In practice, being able to poison an example is almost as good as poisoning a gradient. And you need fancier things to do that, and he'll sort of introduce you to all of that. Okay, maybe this is a good time. Yeah, Milad, if you want to take over and going through your fancier stuff. So, okay, my stuff was sort of like level because I don't like numbers and theory. I'd actually understand theory and stuff, and so he's going to talk to you a bunch about things that like the actual details of stuff.
Yeah, it's not that much more theory, but I try.
Hi Milad, the screen sharing got stopped. So can you retry it?
Can you hear me?
Yeah, we can hear you now. Your screen sharing is not showing though. There we go.
Yeah, no, it's good. Thanks.
Can you hear me now? Okay. For some reason, when I share a screen, I can't speak. Okay.
Yeah, you're
okay.
good.
Okay. So yeah, as Nicholas showed that we showed that like DP HTT is tight under the worst case scenarios, but there are many issues with this. Like auditing technique that we did is that the two main problem that we have is like, first of all, we only showed like DP HTT is tight under the worst case dataset, worst case access, a lot of assumptions that's taken in DP HTT which might not be realistic, and also the kind of the auditing approach that we take requires training many models to kind of get a sense of false positive, false negative, and kind of get good value for like our auditing. So what kind of one question like brings to our mind is that why this is kind of the case, why auditing DP is hard. So if we want to take a look at this, like look at the DP HTT. DP HTT uses the Gaussian mechanism, and the kind of the Gaussian mechanisms, the auditing Gaussian mechanism, like DP guarantees for Gaussian mechanism, like is tied for the kind of the worst case guarantee, which usually happens like near the tail of the distribution. So like essentially what you are doing in auditing, you are looking at this tail of the distribution, and you try to kind of bond these two, kind of distinguish between these two distributions by looking at only the end of their distribution. So it's kind of extremely hard to distinguish these two distributions by just looking at their tail. And so, for example, if you want to, for example, calculate something like in a best case scenario, if you have an algorithm which has an epsilon of 15, you need like 10 million trials to be able to audit in perfect setting. So like it requires training many models. So it's not practical. Like that's the best thing. And this is what I'm trying to solve in like the kind of the next version of this auditing framework that we are working on. So let's me. Second question. So let me like introduce this. Let me introduce this like trade-off function. So like there's a paper in DP called Gaussian differential privacy, which kind of defines a generic form of differential privacy mechanisms. But we start by defining trade-off functions, which says that if we have two distribution P and Q, the trade-off function defines the kind of for each false positive, what is the worst false negative value that we can get. So it will give, instead of like looking at only the tail of the distribution on like this setting, it gives you a false positive, false negative point for for the whole kind of the values of false positive, false negative. So for example, like if you look at this figure, like if we say a function is like, so we can like define a specific curve for a specific DP mechanism. So if we have, for example, an epsilon delta mechanism, and we say, for example, epsilon is equal to something, delta is equal to something, we can clearly plot what is the best false negative that we can get for each false positive. So it's different from just looking at the tail, because why? Because we can just we can audit these mechanisms from all points, not only their tail of distribution. Okay, so how this is useful? Let me give you an example. So one important factor that we have here is that different differential mechanisms have different trade-off functions. So for example, if you have a epsilon delta DP, you get this like dotted blue line here that kind of defines its kind of trade-off function for each false positive, false negative. But for the same value of epsilon, if your mechanism is Gaussian, is not like a generic DP mechanism, you get this red line. So these two mechanisms have the exact same epsilon delta DP guarantees, but their trade-off function are different. So this is an important kind of distinguishing factor between the two frameworks that we talked about. So up until now, everyone that wanted to audit DP, they just look at epsilon delta DP and they try to kind of audit the DP HTT using epsilon delta. But we know this, the mechanism that using DP HTT is Gaussian. So how does that help us? Okay, let's give an example. Let's assume we did all of the experiments that Nicholas mentioned in the previous kind of talk, and we point for a false positive, false negative, or false positive, true positive, and this is a point that we get from all of our experiments. So what we did previously was to say, okay, we have this point, we ran it through an epsilon delta definition, and we get, for example, an epsilon of 0.3. So is it the correct epsilon or not? So we know this is a lower bound on the epsilon delta that we get from the DP HTT. But if we know that the mechanism that we use that we get this false positive, false negative from is a Gaussian mechanism instead of just a generic epsilon delta mechanism, we can we can use the kind of the trade-off function from this Gaussian mechanism and find out, okay, now that for example, the noise that was used in this Gaussian mechanism was, for example, 0.25, and what does that give us is that, okay, if you know that your mechanism is Gaussian, you know that your false negatives have a specific point, then you can get a better guarantee out of this. So for example, for this, so for the same point, by just knowing that your mechanism was Gaussian, you can get, for example, the epsilon lower bound of 1 instead of 0.3. So this is the huge difference between just looking at the tail of the distribution for auditing, or just looking at or using the whole like trade-off function to kind of audit the kind of the whole for whatever point you can just audit the mechanism very good. So, and if you want to,
does that mean that GDP and DP in some sense they're not very comparable to each other because they have different trade-off functions?
DP epsilon DP guarantee is like a lower bound on the so for example, if I'm saying like a GDP mechanism has like an epsilon of 1, what it means that it's always is upper than the trade-off function of the epsilon delta trade-off function. So for example, here these like the solid black line and the dotted the dashed red line are both for epsilon 1. the black line is epsilon delta, the red one is GDP, and there are there are equal for 1 point, which is like when the delta is equal to 0 point something, and but so they always like give you the same guarantee. So you can't get the like they have different trade-off functions, but they epsilon delta are the same.
Okay, so in this figure, according to my understanding, is like you first use this observed point, you get some GDP lower bound, and then you use this GDP lower bound and convert that to epsilon delta DP, which can gives you better bound than directly using epsilon delta DP. Okay.
Yes. So essentially, you don't need to actually audit the epsilon delta. We just like express the numbers in epsilon delta because everyone kind of wants to look at the epsilon delta values. But you can directly just use GDP. Yeah, you don't need to actually.
I guess I don't understand this figure. Why are there two different curves for each case?
So assume assume you're like this point is your observed point. So like so if you want to have a lower bound, like if you know your false positive, false negative is like this much, and you want to like if you don't know any information about your privacy mechanism, and you assume it's just a generic epsilon delta mechanism, you will use this line to kind of lower bound the mechanism. Like say, okay, any point, this is an observed point, so like everything else should be like above this line. But if you know like it's a GDP, you can like use the trade-off function from the GDP. So like these two lines are showing the difference between using GDP and using epsilon delta, and the solid line is just like the equivalent epsilon delta line when you use this GDP. So like if you wanted to get this much, if you wanted to get this epsilon delta DP, you should have seen a point like near right here. So it's kind of very hard to get a point when you have a very low false positive rate or false negative rate. And that's why kind of auditing DP using epsilon delta is hard, and using GDP makes it a bit easier. So I hope this kind of answers.
So it's like the left bottom corner is good, right?
Left bottom corner.
Which direction is good? The left bottom corner is good.
So like anything, so if you go like low, like your false positive rates are getting lower, so it's bad. Actually, you get worse privacy. So you want to be near to the line that goes through 1 to 1, like here, that line between this. You want to be in the center of this figure. That as you are in the center, you have more privacy.
In terms of the auditing point, if you get a curve that goes left and below, then it's better. In terms of for auditing, you want to bring the auditing point down. For the privacy, you want to bring you have.
But I don't understand, why is it this diagonal line from 1 to 1 is good? What is type 1 error? Is that the
type 1 is false positive rate, type 2 is false negative rate.
So but isn't like smaller error the error the better?
So it's
you can think about like if you have the diagonal line from the privacy point, it's the best. So from the attacker's point, it's the worst. So we're basically I think in their work, they're standing from the attacker's middle. So you want to have like curve that close to left side and the lower side.
Corner left side.
So sorry, it's best when you say it's best. Is it best for the attacker or is it best for the?
It's best for the attacker.
Oh.
So for privacy,
you also have curves on top of that. Isn't that even better for the attacker? Like the curves on top of this diagonal line from 1 to 1.
So the curve on top of that is just when you switch your kind of two distributions. Like it's same thing. Like you can just ignore whatever is below above the one, like the diagonal in one.
So I should just ignore all the lines above the diagonal line.
Yeah, it's just like it's defined a privacy region. So like you can't get any like better false positive negative than that, or worse than like you can just change your attack is bad if you get any point above that. Like just you can change your hypothesis to kind of fix the problem. So it's more like yeah, these are the trade-off functions. Like this is the points that we should take. So yeah, so like yeah, this is the main idea that we're gonna use in kind of this to improve the whatever auditing technique. Just instead of looking at this from like just taking the advantage of epsilon delta, we use a kind of a specific definition for the privacy mechanism. One important thing is that like even GDP is not, so like in SGD, as Nicholas mentioned, it's like a subsample Gaussian. So what you do is you take a subset of the data and then you add noise to it, and like then you use this like randomization of the like selecting the data in the privacy analysis. So even like GDP, the Gaussian differential privacy, is not as tight for when you have a subsample Gaussian. So like in auditing, we use the specific the trade-off function for the specific mechanism that we use in the kind of in the analysis. So like there is one more assumption that we know the information about this, about the specific mechanism, but this is like a very common knowledge that everyone uses. Like DP HTT is subsample Gaussian. That's like nothing like very hard assumption that we make, but like this is one more assumption that we use to improve the auditing. So like the first idea is that we use the trade-off function, and the second idea is that okay, now we know that, as Nicholas mentioned, like the GDP is like the DP-HTT is like a repetitive mechanism. Like you take a gradient, clip, add noise, and then repeat this for multiple batches of the data. So instead of like repeating the whole like DP-HTT mechanism multiple times, what we can do is that we can use the repetition of the algorithm to get multiple observations. So like instead of auditing the whole end-to-end process, what we can do is if we have access to the intermediate steps, we can just try to audit one single step of this algorithm. And since we know like if this algorithm is like just repeated multiple times, we can just estimate what's the overall like privacy guarantee. So there are two main ideas that we're gonna use to improve the difficulties of doing auditing. One is using trade-off function, and the other one is just instead of auditing the end-to-end, we can audit each step individually. So okay, so and to put this all together, what we do is that we have this like generic DP-HTT algorithm. The only changes that we do is that instead of having one like taking the gradient and add noise to it, we have two steps. Like we have one from dataset D, one from the neighboring dataset D prime, and we get two observations in each iteration of the training the DP-HTT. And we compute the dot product between the gradient of these two when we have the white box access. Okay. So this is like, so in this way, instead of running the whole DP-HTT algorithm multiple times, we just run the algorithm once. For each iteration, we get multiple observations. So this is what we use to kind of improve the auditing in overall. And so like, let's see how does it improve like compared to the kind of the existing works. So we see that by just auditing using the trade-off function compared to just using the generic epsilon delta, we get much tighter auditing. And we kind of require like in the order of like thousands less kind of observation. So we can like get much tighter auditing with just hundreds of 500 auditing 500 observation. We can get like a kind of very tight epsilon lower one for the P mechanism. So kind of we don't need to train thousands of models. We just need a few hundred observations. So this is the first kind of important factor that like just using trade-off function is very kind of useful in DP auditing. Then one other issue that like we saw previously was that the kind of the final figure that Nicholas shows that it's only tight when we have the worst case data set. It's not tight when we kind of look at the normal, like, I don't know, MNIST data set, CFAR data set, one of these like popular data set. Like it's worse when you adversarially craft your data set. So, but here we show that it's actually, if you use all of these auditing kind of tricks and techniques together and like using the trade-off function, you can get a very kind of tight guarantees even when you use a like normal data set. So for example, when we have a theoretical epsilon of 1, we get like a lower bound of 0.75. So which is like still not 1. It's, there is some gap in it, but the gap is like not that kind of huge. So like this shows that, okay, if you have a more, it might be some kind of, if you have more observation, you get tighter bound, but like still, like you don't need a worst case data set. You can get the auditing, even like a normal data set that everyone uses, that still can leak a lot of information. So you don't get that much by just changing the data set from worst case to like an average case. So this is one point.
I just wanted to ask, you say you have a normal data set, but you are still using like a worst case, and this one change you make in between the two neighboring databases, that's still like you're still using a worst case for that, right?
Yes.
I see.
Yes. I have experiments for that too. Yeah, there was another question.
No, roughly have the same question.
Okay. So what we can do with these auditing techniques compared to like the previous one is that we can use this auditing to actually catch bugs. So like previously what we needed to like train thousands of models to actually do this, but here, since we do per step, we don't actually need to train multiple models, just train. We can implement this as a part of these like privacy frameworks, and it automatically catches bugs for you. So we kind of intentionally implemented a few bugs and try to see if it's easy to kind of capture these bugs. So for one of the kind of the common mistakes that people do when implementing DP HTT is that instead of like you need to clip each gradient individually and then take an average and add noise. But one mistake that people might do is that they kind of take an average then clip. And this is like a huge issue. Like you don't get any DP if you do this. But and here we show that actually if you run our auditing technique on top of this, you get a very, very, very large epsilon, which is like epsilon of getting a empirical epsilon of 30, 40, like empirical epsilon, it means that you don't have any privacy. Like, and like compared to previous work, yeah, you could have like catch this bug with the previous work, but with previous work you get something like epsilon of 5. So you might think that you actually might have some privacy, but here we show that you don't have any. Just like the problem wasn't the auditing, it wasn't the kind of the mechanism, it was just previous auditing techniques weren't as good. So this is one important factor that we can actually capture bugs. For example, one other like subtle bug that might happen is that when you have multiple GPUs, kind of it depends how you add noise. Like if you add noise individual on each GPU, or like or if you like use the same like random noise generator and add the similar noise in all of the GPUs, it can affect the kind of the amount of noise that you add to kind of your gradient vectors. So this is one kind of important case that we can actually use, again, this kind of deep auditing technique to capture these bugs that weren't possible in using the previous methods, which again, because like this is much less, like much more data efficient. It's like
we can't hear you.
We cannot.
Your audio I don't think he can hear us.
I guess the bugs.
message him on chat.
What's the implementation in which you caught these bugs? Is it the same implementation, or you caught multiple bugs, or you tested multiple implementations? Or this is just like some, is this tested on some real world implementation, or?
Yes. So Milad just, what Milad was talking about was that he had some fake bugs they introduced artificially, and that like the people could like have made in the past, but we sort of tested them in these like, in some cases that like they sort of introduced fake bugs in order to see if they could have caught them, and then they went and caught those. But in the past, we have actually got, like we have used this to find, like we have a paper on arXiv where we use this to find some real bugs in some arXiv paper that required training like 1 million models or something, like literally 1 million MNIST models, I think, maybe 1.5 million or something. Are you back?
Yep. Can you hear me? Sorry.
Okay, sorry, keep going. I sort of
yeah, I
pulled
don't
it to you.
Okay, sure. So yeah, so
I'm gonna have
one?
to actually. I'm gonna leave the conference room in a few minutes. So if you want to keep
Sure.
going, yeah.
So yeah, I don't know where did I get disconnected?
Next one, just when you're talking about bugs, like were they real bugs? I said, yeah, like you injected them artificially.
Yep. So yeah, the final one, like this kind of, since we are running out of time. So one important factor is that, as Nicholas said in the previous workshop, if your attack is not gradient vector, is input space, you don't get tight results. Like you have a very huge gap between what you can get using the auditing. But here we show that actually, even when you're limiting the adversary to just be able to inject one kind of input example of one actual image, not the gradient vector, you can still get tight auditing in some datasets, not all of the datasets. For example, for CFAR, for when we use like a ResNet architecture, we can get a very kind of tight auditing, which is interesting. Like, so it gives us, like, we were previously happy that it might be case that, like, okay, when we go from like input gradient to input, we get some privacy path, but it shows that it's actually not true. So this is one kind of interesting finding here that we have. And we also show the same thing for like black box setting, when you don't see any of the internal like steps. So it's not as tight as like the white box setting. So for example, for epsilon of 8, we get something like 1.5, but still getting epsilon of empirical epsilon of 1.5 a low with like high confidence. It's like much better than any of the previous ones. So this is so we show that with these auditing, like DPHGD, with kind of the even with the normal data set and all of the kind of the bad assumption, like not bad, like unrealistic assumption in the analysis, it might not be as loose as we thought. Like this is like a very, it has tight analysis. And so like this is kind of the important factor from all of those our works. That's just it's possible to do auditing DPHGD, and we can implement it as like a kind of bug capturing features. And also, like one other slide that I have might be interesting to some of you is that using the kind of the trade-off function from like the specific mechanism kind of solves some of the issues of finding actual threshold. So you don't need to actually find the exact threshold. You can find any threshold, and it kind of works. So you don't need to repeat like the experiment twice to first find the threshold and then apply that threshold. You can just run, like choosing a threshold of 0 when you use the, like you have white box data is just fine. And we kind of do that for our experiment. So yeah.
May I have a question?
Sure.
So even in the trade-off function way, you still do compute the type 1 error and the type 2 error. And the error itself is represented by probability. So I still don't understand how you can get the number for type 1 error and type 2 error.
So we still like so what the idea is that you kind of have multiple experiments. So for the previous kind of work, we kind of repeated the experiment multiple times, and like we kind of said, okay, we have this many successes. So to detect the, like to distinguish between the dataset D and D prime.
Yeah, I can understand that part, but when you don't repeat multiple times, how do you?
So we still have like the algorithm here is that we have observation, but instead of auditing the whole, like for example, when we audit, like when we implement DPHGD, it's like a repetitive algorithm. And so like we kind of say, okay, the epsilon for each step is like 0.1, and then we repeat this algorithm like 1,000 times, and like we do some composition, and we get like, okay, the overall epsilon is 3. So instead of like trying to audit this like 3 epsilon, we just try to audit the one iteration. And so that since the DPHGD algorithm itself is iterative, our like multiple observations come from the different iteration, not the running the whole DPHGD multiple times. So we still get multiple times, and we can calculate the probability of success.
So you're reading or you're testing one run of the algorithm, but you can get multiple like testing points or testing samples, and then you compute the type 1 error and type 2 error from those samples in one run of the algorithm.
Yes.
Okay.
We also work on like a newer version, which we kind of use multiple points to test each iteration, but still work in progress.
Okay. So for example, you said that if you use multiple points to test the error, so you're basically using something like group privacy theorem, and then you get a upper bound, and then you use your multiple point auditing algorithm to test it against that that kind of bound, something like that.
Yeah, exactly.
Okay.
So like it's not exactly like we don't use exactly group privacy, because like we use a similar idea of like using the trade-off function when you have multiple. So it's kind of you get like a tighter one that like group privacy is pretty loose kind of.
Yeah.